Hi everyone, my name is Victor and I'm going to do my presentation right now for my PhD. And my presentation is called Discovering Causal Links in Log Files Using Machine Learning. Nowadays, researchers use machine learning in several different fields with usually very good results. However, machine learning is very effective in labeling data, that is giving attributes to data, and clustering data, that is grouping data together based on their similarities. However, machine learning is not as good with detecting the root cause of informations. Machine learning is based on the concept of association, not causality. So, to this point, we don't have a very good approach to find causal relations between data. Therefore, finding an approach that works is a very difficult challenge in the field. Log files are one of the main resources that we have right now to track information on systems. They record useful information about the execution of processes and systems using runtime data. And some systems have thousands of log lines that are generated per second, which makes it difficult to identify the most important information among all those lines. So, developing a method that could point the most important log lines among all those ones, and which of those have the highest potential of causing problems, could be a very useful asset for the industry. To help with this task, a recent field is called causal structure learning, or CSL. CSL is composed of many algorithms that are able to identify the effect of an experimental intervention given observational data, or a combination of observational and interventional data. So basically what we do is we try to identify the effects on a given dataset of introducing or removing pieces of data. So, to achieve this objective, we will use the CSL methods to identify causality between log lines. But this task is not trivial. To get to our goals, we have planned 3 steps. Our first step uses log parsing. Log parsing, for those that do not know, is a process in which you separate static fields from variable tokens in a given log line. And our first research hypothesis is that after log parsing, variable tokens will carry a significant weight to detect causality between the tokens. In our example, we have 4 log lines. Seeing those 4 log lines, we can identify that lines 1 and 2 are connected and the lines 3 and 4 are also connected. However, the computer must also learn that. So, after parsing the logs, we can use the common tokens, the common variable tokens between the lines to track the causality. So, our intention is to create a new parsing approach that saves the variables, instead of just replacing them as a normal parser would do. And after our bibliographic review, we saw that usual parsing methods consider only a local window of words, instead of using the whole text and its dependencies. So, we will adopt the transformers architecture, which process the whole text as an input, and are capable of tracking dependencies in the whole text, instead of just considering local windows of words. The steps of our parsing method are as follows. First, we tokenize and clean text using state-of-the-art technologies like SentencePiece from Google. Then we use transformers, that we mentioned earlier, to create the embeddings, with the whole text of the logs as the inputs. Then we cluster the data from the embeddeds into subsets. In our method, we are clustering the logs in order to separate log sequences, gathering similar sequences together. Like in this example, we have many raw log lines, and we will cluster them into 3 different subsets. Each of the subsets has similar log lines. In our method, after the clustering step, we count the frequencies of each token in a given cluster. Then, we can establish a threshold that may change for each dataset. Tokens that have frequencies below this threshold are considered variable tokens. If they have frequencies above this number, they are static fields. All the tokens are then saved in a database, specifying their type, so that we can use this information later. In our example, we can see that package 2 and package 3 are the variables, since they appear less times. In our second step, we are presuming that central nodes are more relevant to the appearance of other log nodes. To identify that, we have to generate a graph from the sparse log lines that we have in our dataset. But this task is not easy, since the tools that are available to create graphs from raw data are generally adapted to deal with natural languages and not to deal with log lines. We can see an example in this picture. Using our previous example with 4 log lines and 2 pairs of variable tokens. An approach would be connecting those pairs. We can connect them, and each of the log nodes is connected to a node that begins all the graph and another node that ends all the graph. Then we have a graph generated from the log lines. This is a very basic approach, and we intend to research in our project other several approaches and find the most robust ones. In our third step, we are going to use the CSL techniques to iterate on our graph. CSL usually receives an undirected graph as the input and returns a directed graph, in which we can see the arcs, the directed vertices, between the log nodes. Our main intention as the result of our research is to generate a matrix of causality, indicating the probability of causal links between each pair of nodes. Thank you. That was my presentation. Any questions?